Okay, so today we're going to talk about chapter 8 and chapter 9. Both of the chapters kind of lump well together because they're so similar, right? A lot of the stuff we'll talk about basically works whether you're talking about bricks or you're talking about concrete masonry units or you're talking about stone. It's kind of all the same thing. So it's a good set of chapters to lump together. Likewise, if you've looked and actually done the reading ahead of time, you realize that there's a lot of pictures in these chapters, right? And a lot of big pages of diagrams where you see a whole bunch of different concrete masonry units, right? And they label what they all are. So what I will try to do today is distill it down into the basic information so that you have a better understanding of how these buildings would go together. Unfortunately, or fortunately, depending on how you look at it, there's not too much of this style of building around here. So it's hard to go out and get really good concrete examples. Certainly the building we're in is made of brick, but we're going to talk, it's not really solid brick, right? It's a brick veneer, so that's more of the common way we're going to see brick around here. The chances of having a completely brick building, fully structural, is very unlikely around here. It happens, there's a few, right? And we'll talk about those in depth as we go along. So in order to talk about brick, we have to first talk about mortar, right? And this is kind of the most important part of masonry construction because it's what glues all of the pieces together. So if we didn't have this glue, so to speak, none of this would even work, right? And so the idea here is the mortar is this stuff, right? It's the stuff that holds the bricks or the concrete masonry units or the stones together, right? And it provides the cushion between the masonry units. It gives full bearing capacity, right? So we can put the full weight. It transfers all the weight through from one brick to the next brick, right? And it compensates for any weird surface irregularities or imperfections that are in the brick. Certainly, if we're talking about brick, it's more of a consistent product, right? But if we were talking about stone, for example, which we'll talk about in a bit, it's far more irregular, and we need something to kind of absorb those irregularities, right? It also provides the primary seal between the units, right, to keep out the wind, to keep out the water, right? So it's sealing off the building, not letting you have those air gaps. And it's going to bond all of those individual small little tiny pieces into what would theoretically be a monolithic whole or a monolithic wall, right? And so we have a few issues with that in earthquake country, and we'll talk about what those are as we go along, right? So if we talk about the basic ingredients to a mortar, right, it's a lot like concrete, right? We've talked about concrete at length. You guys should all be very familiar with it by now. Mortar is just kind of a variation on that. It, again, has the Portland cement in it, which was one of those critical components to concrete, right? It also has what's called hydrated lime, which is kind of the additional piece that's not in concrete. And this is for the workability of the mortar itself, right? It's to make it a little bit more flexible when the masons are working with it, right, without decreasing the strength too much, okay? There needs to be some form of an aggregate, which we know from concrete is providing a lot of the structural space. It's filling up, right, the spaces in between the cement. In this particular case, it's going to be a sand. Usually it's a fairly coarse sand, depends on your mortar, right? But we need something to take up the space, right? At the same time, we're not going to use, pea gravel or little pebbles as our aggregate because it's too big, right? So we need it to be small enough. It's not usually something as fine as, say, like the beach sand in California, right? That's very fine sand. This is going to be something a little coarser than that in terms of aggregate. And then obviously we're going to add water to it, right? So if we talk about a little bit of the specifics here, hydrated lime is something you're not that familiar with, right? I kind of glossed over Portland cement. You should remember that from the concrete lecture. Hydrated lime is limestone or seashells, right? Wherever we get the lime, right? That's burned, leaving what's called quicklime. Okay. After that, you go through a process where it's allowed to absorb as much water as it can hold, right? Which is kind of this weird thing. It's called slaking, right? And that results in what's called hydrated lime. So it doesn't mean that it's like wet slush, right? It just means that the powder that's very, very dry to begin with is allowed to absorb water, right? And so that's where we get hydrated lime. Okay? There are, just like in concrete, where we had different strengths to our concrete, different bearing capacities to our concrete. Mortar has the same sort of thing here, right? Where we have a variety of types. I will not ask you the specific types of mortar, right, and to be able to distinguish them. I want you to understand that there are general types to mortar, right? Type N is the general purpose type. Type S is a higher bond strength. Typically, it's for an exterior load-bearing condition, right? Type O is the opposite. It's the low-strength, non-load-bearing condition. It's kind of the decorative mortar, so to speak. And type M is the highest strength mortar, right? Has the least workability, right? You should remember this from the concrete lecture, right? The more workable something is, tends to be the lower strength it is, right? So this has the less workability, but it's for any kind of high lateral compressive loads, right? Big loading conditions. So not that you really have to remember these. You can look these sorts of things up in a table, right? But it gives you some idea of the compressive strength after 28 days, going all the way from 2,500 psi down to 350 psi, just based on the mortar that you've used, right? So the book cleverly points out this little acronym thing, Mason work. It's every other letter, and it goes from highest strength to lowest strength. Why you have to remember these sorts of things, or it suggests that you remember these, I don't know. This is the kind of thing that you look up anyway, but you at least get the idea, and maybe it'll stick in your head anyway, right? So the higher the strength of the mortar, the less workable it is. That's exactly what we've been talking about. If you're choosing a mortar, you want the lowest strength mortar, right, that will meet your structural requirements because it's the easiest to work with, right? So you're not going to be doing a project and say, oh, well, I better just pick the highest strength, right? You want to really understand what strength mortar you need and pick the mortar that most closely represents what it is you're trying to get out of it, right? And that'll give you the most workability, right? So modern masonry mortars are made with hydraulic cements, right? This is what we're talking about with Portland cement. Basically, by saying hydraulic cement, that's what we mean, is that it's Portland cement. And the idea here is that the cement, right, cure is a chemical process. It's the result of this hydration. Remember we talked about this, where it consumes the water, makes a crystal structure that bonds the aggregates and the other components, right? So in concrete, we just had aggregates. Here we have bricks, right? But we have to be able to bond the bricks together somehow, right? So it's a chemical bond, right? Before we had hydraulic cements, mortars were made without the Portland cement. It was just lime, sand, and water. In that case, it doesn't have a chemical bond, right? So it's not bonding it together in the same way. Right?
Is that considered type K when it's just lime, sand, and water?
I don't know off the top of my head. I'd have to look it up and see. So mortar hydration is the complex set of chemical reactions, right? Just like in concrete that we talked about. It results in the dense, strong crystalline structure that bonds all the components together. Once the hydraulic cements harden, right, they become insoluble, right? You can't wash them off with water anymore. Okay? So, as brick is a product of fire, right, it is naturally the most resistant building product we have to fire, right, which is kind of an interesting concept. Okay? A typical brick is shaped roughly to fit the human hand, right? And so I've got a bunch of bricks that I'm going to start passing around. I will keep a few of them up here to use them as examples, right? But it's helpful if you start to actually hold these to understand what's happening. Now, as I pick these up, right, and you pass them around, you'll see some are lighter than others, right? Some are bigger than others. They kind of have a rough shape where they tend to fall, right, in a certain category. But all of them should be relatively easy to pick up with a human hand. Here's an example of one that's slightly bigger, right? So if you have slightly bigger hands, this one's easier to work with, right? So it's helpful, though, to have some of these passing around so that you can see these. Right? Obviously, they have different colors, and we'll talk about that in just a second. Right? Let me keep one up here. Right? We'll pass these two. Right? And you can keep that one going, too. And I'm going to hold on to one. Right? So the thing about a brick is it's really easy to work with because it's pretty small. Right? If I can pick it up with one hand and kind of toss it around and move it, right, that's a good sign if I'm building with it. Everyone in this class can pick up one of these bricks and work with it. right? They're relative compared to the things that I passed around or some of the things that I will pass around. These are relatively easy to pass around, right? And that's kind of the point, right? They're also really flexible for small-scale geometries, right? And by small-scale geometries, I mean if I want to make a tight little arc, right? These are relatively small pieces, right? I don't have a big piece. Like if we look at, by contrast, one of these concrete blocks, right? It's much heavier. It takes me 2 hands to lift. And if I were to put these together, right, it would be much harder to make a tight little small geometric piece. Does that make sense? Right? So because these are small, we have a lot of flexibility in what we can make out of them, right? Also because they're small, they're much less likely to crack during the manufacturing process, right? Which is really important because if the brick cracks, it's not worth anything to us, right? And so we will grind it up and make something else out of it. So the other thing about brick, right, and if you do a Google search for this, right, Google image search, you can find tons and tons of examples, is that bricks can look very, very different depending on the type of brick. And I've passed a bunch of different bricks out to you guys, so you can already see that there's a whole bunch of differences in color, size, texture, right, and general look. We can look at something like this, and you can see there's a bunch of different looks here, right? The bricks that are used in this building look very different than any of the ones that are up here on the board, right? So they're really going to change depending, and that gives you a lot of flexibility in terms of the look of a particular building, right? So let's talk a little bit about brick manufacturing, okay? So if you think about something like this, right, if we had a whole pallet of bricks, these are pretty heavy, right? So it's probably not the kind of thing that you want to buy, say, Fijian bricks, right, and have them shipped here from Fiji, right? Or, oh, I'm going to really, get some fancy bricks. I'm going to buy bricks from Italy, right, and I'm going to import them, right? They're too heavy to bring from a long distance off. So what happens is, because of their weight, right, they're going to be made in small quantities at local plants, somewhat near wherever it is you're going to try to do your building, right? So, for example, if I were going to go to Home Depot and I were going to buy some bricks, right, chances are that the bricks that are in Home Depot in California come from a different source than the bricks that are in Home Depot in, say, Rhode Island, right? Because they don't want to have to ship those across the country. Yeah. What? Okay. So that would be where the bulk of our bricks come from. Exactly. So this is the kind of thing that's important, though, because they're not going to export. Bricks are not an export quantity, right? We're not going to export the bricks to China. Right? It doesn't work. And so it's important to realize that these are locally made, right? And so I'm glad you brought that up. That's great, right? They're also going to be made from local materials because, again, bricks are made primarily from clay, which we'll talk about. You don't want to be shipping the clay from somewhere to make the brick, right? You want to have a relatively close source for this stuff, right? So the raw materials are going to be dug from a pit, right? They're going to be crushed into a nice fine powder, right? The powder is then going to have water added to it to make basically mud, right? A clay, so to speak. And it's going to be formed, the brick is going to be formed using one of 3 processes. And we'll talk about these 3 processes in the next several slides. The first is called a soft mud process. The second is a dry press process. And the last is a stiff mud process, right? And they're all slightly different, and they're all based on whatever raw materials you have that you're going to make the brick with, right? And so depending on the quality of the materials you're going to be making the brick with, you want to use one or the other of these, right? So the first one, which used to be the most common, is called the soft mud process, right? And this is probably the easiest to make because it contains the most water, right? So you don't want a clay that expands and contracts a great deal with water, right? You want a relatively stable clay to begin with, right? You're going to add 20 to 30% water to this clay, right? And then you're going to pack the clay into a basic rectangular form, right? It can be done by machine, right? So you're using machine to pack the clay in, or it can be done by hand, right? So if we go into the most simple way of making a brick, right, you would have some kind of a rectangular form that looks something like this, right? You'd have a batch of clay, and you'd pack that into this form, right? Afterwards, you'd remove the form, right? Leave your bricks to dry, something like this, and then reuse it, okay? If you want a little bit better surface, so something like this is a good example of that. You guys all were so nice and brought all the things back up, but I'll pass them out yet again, right? You might have something like this, which is called a water-struck brick. So if you look at this surface, it's a much smoother surface, right? And the idea behind a water-struck brick is that you dunk this formwork in water ahead of time, right? So it has water right on the surface, right? And when you do that, right, it helps to consolidate the surface of the clay a little bit and give it a smoother, denser surface right on the surface. So if you look at something like this, right, which since I only have one that's a good example of it, I keep walking back here, right? But if we look at the face of the brick here, right, it's a very different smoothness than the edge, right? The edge is what we're going to see when it's in the final building, right? So this is the part that's water struck, right, because it's that smoother piece, right? So I might as well pass this one around. I'll start holding a different brick, right? And you guys can see that one. Okay, I can hold this one for now. Somehow it feels better when you're talking about bricks to hold one in your hand, right? I should make all of you hold one in your hand while we're talking about it, right? So this is what the water-struck bricks looks like. It's easier to see it in actual, because you could tell the surface difference, right? It should be relatively obvious once you hold it, right? Okay, so we move from that soft mud process into the dry press process, right? And so this is if we're using clay that shrinks a great deal, right, when you pull the water out of it, right? So it's when it has big expansion and contraction that we need to worry about it. And the difference is the process uses much less water, right? So in the soft mud process, we had 20 to 30% water, right? Now we're going all the way down to just 10% water. Much, much less water. Because of that much less water, it's much harder to work with the clay to begin with. So we're going to use a machine to press that very dry clay, right, into steel molds, right, at very high pressure, right? So the least amount of water, right, but it takes the machinery. You have to press it in. You can't make it by hand, that sort of thing, okay? So we move into the third option, which is the hybrid, right? It also tends to be the most efficient in terms of production. And so this is the most widely used method today. It's called the stiff mud process. And we have less water. It's 12 to 15%, right? So it's not as little water as the 10%, right? But it's not as big as the 20 to 30% of the soft mud process. So we're kind of right in that middle ground, okay? The clay is passed through a vacuum to remove as much of the air pockets as it possibly can, right? Now, if we look at any one of these bricks, right, there are still some air pockets in it, right? That's the nature of the material. But we're going to try to remove as much of those as we possibly can, right? Once we've pulled all the air out with the vacuum, right, we push the clay by machine through an extruder die that gives the brick its shape, right? So basically it's a rectangle. It's like pumping icing through one of those little icing bags if you cook or make cakes or whatever, right? You push that material out through the extruder die, which is right here, and it makes a big, long, continuous brick, so to speak, okay? And what we can do is then we can have an automatic cutter that as this comes out, right, of the end of this extruder, right, we can pass a wire through it, right, and cut it up into individual little bricks, right? And so this process can make a lot, because it's a very automated process, we can make a lot of bricks, right, which is part of the advantage and why it's the most common today. So if we continue on in the manufacturing process, after we have the brick that is the shape that it is, right, it's still just made out of clay. So it's still a very pliable sort of material, right? It's not in its final form. It can't bear any weight yet. So in the old days, right, before we started firing these bricks and stuff, in California, right, anybody have a house that was made out of adobe? Yeah, a few people maybe, right? In Mexico maybe, right? Adobe bricks were very common in the state of California. Basically, we were taking the clay, and instead of firing the clay, we just let it dry out in the sun, right? And that made the adobe brick, which is a mud brick, so to speak, okay? But we want to take it a step further. We want this to have more bearing capacity. We want it to be more fireproof. So what do? Right? We have to, number one, get the bulk of the moisture out of it before we can actually fire it. So what we'll do is we'll put it in a kiln and try to dry it out for 1 or 2 days, right? If you don't have access to a kiln, you could dry it out in the sun, though you have to worry about, is it drying evenly on both sides? Is it shrinking more on the top? That sort of thing, right? And then we're going to continue on in the process, right, to its firing and finally its burning, right, which we'll talk about in a second. So this is an example of a brick factory. The brick factory characteristic is typically the long chimneys, right? Very common to see those sorts of things. Bunch of individual pictures kind of in the brick manufacturing process. I have more specific examples down the road that you can see. So if we're going to fire the brick, right, so we've already kind of kiln dried it out, so we've got some of the moisture out. It's in its final form. We need to then proceed with firing, right? And so before our modern kilns that were more efficient at this process, what they would take is they'd take all these individual bricks and they'd stack them in a loose array, right? And the idea being that there is some airspace on each side. Obviously, it can't be completely airspace because the bricks, when they stack on one another, have to touch each other, right? But we want a lot of airspace in between to allow the heat to come around all of the bricks, right? This loose array was called a clamp, right? And so after that process, right, we wanted to seal the heat in some way, so they'd cover it with kind of a dome of dirt, so to speak, or mud, right? And that kind of seals the heat in. They'd allow space at the bottom, right? So something like this, right, for whoever's tending the fire to be able to stoke it with new burning materials, right? Whether that's something like coal or something like that, or whether it's wood, depending on what you have access to, right? So we have this kind of loose array that's inside here. It's been covered with mud, and then we light a fire underneath, right, to start the process, right, the firing process. So the fire is generally going to be maintained for several days, right? So this is not like a short process, not a quick flash fire, right? It's a long process, right? After it's cooled, right, they'll open up this and start to sort through the bricks and pick out the ones that were fired evenly, keep those as the best ones. The ones that were on the edges that might have been fired somewhat unevenly, maybe they can use in less desirable places in the building where you can't really see them, or the internal structural places. And obviously, if they cracked or had some problem during the manufacture, those are the ones that get tossed out, right? So this is actually in one of those kilns, lighting it, right? So you obviously have to light it. Yes, sir. Brick and so, well, it's a good question. There's usually enough space around it that you're not trying to pack it in so that it's so dense that you're covering it up, right? Once you get down and you've dug out enough, you get to the point where you have the brick shapes, right? And the ones on the edge tend to be kind of screwed up, so you toss those out. It's the ones on the inside that you get to.
But the ones that you toss out, like, what do you do with them?
You're
Like the ones that aren't even.
yeah, the ones that are not, that have cracked or something, they're basically garbage, right? And so to the extent that we can grind them, in modern times we'd grind them up and use them as like base rock or something for a freeway or whatever. It's just like leftover concrete pieces, right? You'd find a way to reuse it, right? In this time, or not necessarily, this is modern time, but they're doing it kind of the old-fashioned way. They may not have access to the machinery to grind it up to use it for base rock, so they may find another way of using it. Maybe it's just the retaining wall or something that is not truly structural but can be used in some way. Okay, so if we're talking about the firing, it goes through several stages, right? So the first stage of firing, this is that process of heating the bricks, right, and cooking the bricks, is what's called water smoking and dehydration, right? So we had, if it was the soft mud process, we had 20 to 30% moisture content. We need to get more of that moisture out, right? And if we were down in the stiff mud process, less moisture, so it takes a little bit less time to do this. We're removing as much of that water as possible, okay? After that, somewhere between 1800 and 2400 degrees, we're going to go through the oxidation and vitrification process, which basically changes the clay. It's like, how many people, when they were kids, like played with little clay in art class, right? And you made like a little head or a turkey or whatever it is that your teacher had you do, right? And then once you made that little thing, you stuck it in a kiln and it became a hard object, right? The same thing happens in brick, right? Where it's going to transform from that clay, that mud, right, into a ceramic material, into something that's actually hard. Right? So the firing process is transforming the material, right? Afterward, right, after we have that primary, ceramic transformation, We may quickly add more color, blasts of cool, add more heat, right? Blasts of cool air, something like that, which can change the color, right, of the bricks themselves, change the surfaces of the bricks themselves slightly. And so that's a process based on whatever your raw materials are and whatever your manufacturing process is. Okay? And then finally, you're going to try to cool it in a very controlled manner to control color, right, and to avoid thermal cracking, right? And so if you're doing it, in the very old-fashioned way where you have a loose array of bricks, this is much harder to do, right? But if you're doing it in the modern way, right, where you're going through a tunnel kiln, you have much more capacity to control how this stuff happens, right? So this is a much larger brick kiln, right? A lot more holes on the side to be able to stoke it and get the fire underneath it, right? The more times these are used, like that picture that I showed a while back, that's more of a loose mud. You kind of cover it in. Something like this, right, is starting to be a pretty formal kiln, even though you're still covering it basically with mud bricks. It's something that's going to be reused over and over again. You kind of have walls that are more permanent in their design, right? After the firing process, right, you're going to go through and inspect all of the bricks for defects, right? Make sure they don't have cracks, that sort of thing, right? And then you're going to pack them up for shipment to wherever they're going to go, right? So we have them packed up on a pallet to get to the actual job site. From start to finish of making a brick, somewhere between 40 and 150 hours, right? So it's really not that long. It could be less than 2 days, right? So it's a pretty quick process, which is a good thing, okay? So the thing about brick sizes is there isn't a standard size for a brick, right? There isn't like, I can't just say, okay, a brick is X, right? And you should have noticed by all the ones that I passed around that there is a rough size for a brick, right? But if I were to compare each of these bricks side by side, you'd find that each one has a slight variation, right? This one's thicker, this one's a little bit longer, right? If I compared, say, this one and this one, right, those two are different, right? This one's longer than that one, right? This one, they're starting to get fairly close. It's a little longer, right? The point of showing you these things, even the heights are slightly different, right? These look like they're really close, but they're slightly different, maybe a 16th or an 8th off, right? All of those little variations occur in the brick. So if you're going to design a building that's made out of brick, right, you really need to know which exact brick you're going to use, right? So you would go, let's say you're an architect, right? You would go pick the exact brick so that you can design your whole building around that particular size, right? And so typically speaking, right, we're looking at 3 courses of brick to be somewhere right around 8 inches, right? 3 courses of brick with mortar is going to be somewhere around 8 inches. Though, right, if we look at this wall and we count up 3 courses of brick, that's a lot larger than 8 inches, right? So just because I say that it's typically 8 inches doesn't mean that it's universally 8 inches, right? And I think that's a really important thing to understand when we're talking about bricks is they're not all the same, okay? So the lengths of brick, which I just showed you in those examples, can really vary, right? And the thing that is often glossed over by this is that it can completely change what your building looks like from the outside, right? If you have longer bricks, your building's going to look shorter and squattier on the ground. If you have shorter bricks, your building's going to look taller, right? So you as a designer have that kind of control over what your building's going to look like, right? This building looks a certain way because it has a certain pattern of bricks, right? I would argue that these are pretty long bricks, right? Which makes this building seem even broader than it would otherwise be, right? So you as a designer just want to be aware of that and pick the brick that best represents the type of building you're trying to design, okay? Oh, the other thing I should say is obviously the larger the brick or the longer the brick, the fewer joints there are, the less labor it's involved in making the building, the cheaper the building becomes, right? So there are certainly advantages to picking a bigger brick. Right? So a facing brick, right, can be a non-structural brick or it can be structural, right? And the purpose of the facing brick is where you're going to see the face of the brick, right? It's for looks, right? So it's the most valuable because it has the best surface, right? We can't hide any imperfections. It's the one that you're going to see, right? So you're going to make sure you only use those facing bricks where they matter. Okay? We also have what's called a building brick, and that's going to be used where your appearance really doesn't matter. Right? So I could bury it somewhere inside a wall. It still performs its primary structural purpose, right, in terms of supporting weight or handling lateral loads or what have you, right? But it's not going to be seen, so we don't care what it looks like, right? And I don't have the best examples of that. You know, some of these are worse than others, right? Some of these I think are done relatively intentionally, right? But it could be something like this where the surface just really didn't come out right, right? And you're going to try to bury that somewhere inside the building. Like this side is fine. This side is kind of wonky, right? My guess is that this was actually manufactured with that kind of a surface on it for the look of the building, right? But I'm trying to pick an example. Maybe this is a good example, right? Where we've got some cracks like this, right, that really aren't desirable, right? Probably not going to see the end of this brick, but you at least get the idea of what I'm talking about, right? So it's something that's less than desirable. We've got something here where we've got a crack running up of it. That would probably be less than desirable, right? So both types are solid, right, which can include either cord bricks or frogged bricks. And I'll talk about that in just a second. Okay? So we have three different types of bricks that can be made. Okay? This first one is called a cord brick, right, which basically means it has some cores that have been removed from it. So I have a couple examples here of cord bricks, right? They're typically the round circles. Okay, so I'll pass those. You can see those. Right? These are considered structural bricks, right? If we move over, right, into the hollow, right, which I don't really have the best example. This one's probably the closest, right? The holes are getting bigger, right? A hollow brick doesn't have the same structural value. So it's something that you're going to be using on like a brick veneer or a non-structural wall, okay? And in a hollow brick, you can remove up to 75%, if I'm getting that correct, right? 60% void, right? So you can remove an awful lot of the brick, right, because it's not a structural brick, right? The last type is called a frogged brick, and I passed a few of those around, and I was holding on to one a second ago. But the frogged brick just takes a piece of the surface out. Now, the two examples that I'll pass around are only one-sided on the frog. Some of the bricks are two-sided on the frog, right? But it's this little depression on the outside of the brick that removes some of the weight, right, to reduce shipping costs, right, but doesn't harm the structure of the brick itself, right? So that's that last example over there. That's frog, right? So cord and frog brick, right, are considered to be solid brick, even though they aren't actually solid, right? Has a bearing surface as at least 75% the size of the brick, right? So this border around here needs to be 75% of the face of the brick, right? Which lets us remove that middle section slightly. Or if it's the cord brick where we've taken out those little circular cores, that still gives us 75%, right? And so this reduces the volume of and the thickness of the clay, right? It allows the bricks to be fired more evenly, right, more consistently in the process, reduces problems during the firing process, right, because they're going to happen more easily, right? It reduces the fuel costs to transport these bricks to the site, right? And it obviously reduces the firing costs because it takes a little bit less time. So it's a pretty good advantage to this whole system, right? So a hollow brick can be up to 60% void. So we see there's an awful lot of void there, right? It can allow for rebar to pass through the hollow bricks, right? And it can give you a single withe, which we'll talk about in just a second, right? Which is basically one vertical row of bricks that can actually kind of withstand structurally, right? So it's not structural in terms that it's not load-bearing, right? But it can support itself and provide like a veneer on the surface of your building, right? So this is the kind of thing that's more for looks than it is for actually structuring the building in the first place. Okay, so we have to talk about terminology, right? And these are the kinds of things that if I were ever going to test on a test or a quiz or something like that, what I would do is I would give you a list of these are all the terms, right? Here's the blanks, right? And there's maybe 8 blanks. Pick 4 and label them, right? So you have some flexibility in terms of you could pick, you know what a course is, you know what a withe is, but you forget what the difference between a soldier and a rowlock was, so you skip that, and you do a stretcher instead, right? And we'll talk about what all these are in just a second. Unfortunately, in a class like this, there's always a lot of terminology that we have to go through, and part of the point of taking a class like this is that you're knowledgeable enough to understand what these terms mean, right? So when we get to wood and we talk about, what's a stud, you understand what a stud is, right? Or if we talk about what a joist is, you understand what a joist is. This is the same thing as understanding a joist or a stud, except it has to do with bricks, right? So if we start to get into the terminology, right, a withe, right, is one vertical row of bricks, right? So if we think about like a brick veneer on a building where it's just one brick deep, right, that would be one withe, right? Likewise, right, we have what's called a course, right, which is one horizontal row of bricks, right? So a particular building would be made up of lots of courses of bricks. Make sense? Yeah? Okay. So we talked about what 3 bricks plus their mortar joints would typically be. 8 inches, right? So again, that's a general term, right? But it gives you some idea. So if you're a designer, right, and you're trying to decide, I'm going to make a brick building, even if it's a brick veneer building, right, what do you think about? How do you decide what bricks you want to do, right? So the first thing you want to think about is, what is the molding process that made the bricks in the first place, right? Was it a wet struck brick? Does that mean it has a good surface to it, right? What kinds of raw materials do I have? What's that going to do to the process of the bricks and how they're going to look, right? The next thing that you're going to be picking is the color of the brick, right? You guys have probably been on BART, right? You've been through the Oakland stations. You notice that, and I forget which one's which, right? One is blue brick, the other one is red brick, right? The stations are completely identical except for the fact that one is blue and one is red, right? So you as the designer, right, picked the color of the brick to help people understand which station was which, right? And it makes it easy because you understand, oh, I get off at the blue station or I get off at the red station, right? And so by changing the brick color, you as the designer have control over what's happening, right? Likewise, you're going to have control over the size of of the brick, right? Which is going to translate to what the building looks like, right? Is it a long, stretched out building? Is it a really tall building? What does it look like? And also, because of size, how much is it going to cost to make it? How many joints are there, right? Those kinds of things. So the last two, which are brick grade and brick type, right, we'll talk about a little bit more, but they have to do with what are the actual capacities of the brick, right? So a brick grade establishes the basic minimum requirements for compressive strength, right? So how much weight can they bear in compression, right? And also water absorption, right? How much water can absorb into these bricks. Obviously, we don't want too much water to absorb into the bricks, right? Then we have brick type, right? And so brick type defines limits on the variation brick to brick, right? So it's variation in size, right? So how much do they change in size, right? How much distortion in the overall shape is acceptable? How much chippage, corners broken off, that kind of thing, is acceptable, right? And how much damage can be done to the corners. So if we look at this particular slide, right, we have fairly consistent, right, bricks, but then we have one like this where the corner's been knocked off, right? This is within the type that was allowed, right? So we can have a couple corners that are knocked off, right? You guys have probably seen bricks that have been tumbled ahead of time to look a little bit more worn, right? Which would be the complete opposite of, say, these bricks, in which no chippage would be allowed, right? So the type is going to allow you to specify what's acceptable and what's not acceptable, right? And so we have our grades and our types here, right? This is the kind of thing that you can look up. I'm not going to ask you on a test, true, false, type FBX is the least variation per unit. Like, that's too specific, right? I want you to have an understanding that there are types and grades, right? But the specifics don't matter, okay? So let's continue on with terminology a little bit, right? And so we're going to go through, and I'm going to talk about these, and then we will get to a slide where it's a bunch of blanks, and you can try to figure out what they are, right? So if you printed the slides ahead of time, you can fill it in. If not, you'll have to do a little drawing, right? So the most basic brick the brick that we tend to see on the outer surface of a building is called a stretcher, right? And so it's this brick, right? It's lying down in its horizontal position, right? It looks like these. So that's called a stretcher, right? A header is when we take the brick and instead of running it along in the long position, right, we rotate it and put it across two withes, right, to tie those withes together, right? And I'll show you a bunch of examples of how the pattern can vary on bricks and why the pattern varies in just a second, right? So then we move on into what's called a soldier, right? And a soldier is a brick that's standing on end, standing up. To me, for whatever reason, soldier is always easy to remember. They just seem obvious because they're standing up, right? So its face is going to still be parallel to the wall surface, but it's standing up on end, right? And so typically you'd see these above like doors, right, and that kind of thing. That's typically where they'd fall in a building, right? And the last piece here is called a row lock, right? And so we've taken the brick and we've flipped it up on end, right? So we have a little bit more in the height here, and it's running across, right? Once again, across two withes. So we have different joints, right, that vary. We have what's called a head joint, right, which would be at the ends of the brick. We have a bed joint, right, and these should be relatively easy to remember. Bed is what you lay in. It's what the brick lays in, right? If you're laying down, right, your head is at one end, so that's your head joint. See, I'm helping you guys remember this, right? Bed joint, head joint, right? A course, we already talked about, is this horizontal row of bricks, right? And a withe is the vertical row of bricks, right? And this last joint is a collar joint. I have no special way of teaching you that. It's just a collar joint, right? So this would be the kind of thing that might show up on a test, right? But I wouldn't give it to you as completely blank like this, right? I would give you this diagram, and then I'd give you the list, right, of row lock, right, head joint, bed joint, soldier, stretcher, course, withe. What else? I'm forgetting something else. I said row lock, header, right? So spend a little bit of time, right? I'll write out the list right now if I can remember all of them, right? And see if you could actually do this. I know I just went through it, so it's a little unfair. You haven't studied yet, right? But you ought to be able to at least do the head joint and the bed joint, right? Head joint, bed joint, stretcher, soldier, row lock, what's the last one? What am I forgetting? Header. We have a collar joint. Collar joint. We have a course. We have a withe. So shoot for like 4, right? Maybe 5. This is pointing to the joint. This is pointing to the joint, right? This one's pointing to what this would be. No, excuse me. This is pointing to what a single row going that way would be, right? This is pointing to what a single row going this way would be, right? That one I'm never going to test you on, right? That one is pointing to this piece, right? This one is pointing to this piece. That upper one is pointing to this one that's standing up, right? This one's flipped up on end. So what do you think? Could you do it? Could you get 4? Get all of them. I like it. Right? The question is, can you get all of them next week? Right? Actually, to be honest, I haven't written the test. I don't know if it's going to be on it, but maybe it should be. Maybe it should be. Sounds good, right? Sounds good. Okay, so here we've got some answers, right? So these are the ones that were easy, right? Bed joint, right? The brick's laying in it. Head joint is where the head of the brick would be, right? Collar joint is the joint in between these two. Sometimes it's the learning what the diagram is pointing to a little bit, right? So if this were a test and you really didn't understand what something was pointing to, right, come up and ask me what it's pointing to, or make a note that says, I think this is pointing to this particular joint, right? So yes, on a test, you're doing all your answers on a Scantron, right? But if you write notes on the physical test itself, right, you can go back when you do your test corrections and remember what you were thinking about a particular question, right? Likewise, I'll page through it and take a look at what notes you already had on your test and that sort of thing. Okay? So, right, course, right, wide is that vertical one. Okay? We're never going to look at what a blind header is, so ignore that, right? Header, right, laying flat, it's a header, right? Stretcher is laying flat along the length of the wall. Soldier is standing upright, right? And a row lock is turned up on edge. Okay? So, again, if I were to ask something like this, I would be asking for, pick 4 that you know, right? Or 5 that you know, something like that. So, the thing about brick is depending on how we lay the brick in the first place, right, we can have a very different pattern to what this brick looks like, right? So the simplest pattern out there is called a running bond, right? It's used primarily in veneer walls, right, or walls that have some kind of an internal cavity, right, because it doesn't have any way of tying multiple wides together, right? So it's something that's just on the face of a building, right? And we recognize it like this building, right, where it's kind of that continuous brick pattern, right? If we were to pick the basic brick hatch in AutoCAD, it would look like this, right? It's like just the generic, right? We can move from that into what's called the English bond, right? And the idea behind an English bond is we have one course, right, that looks like that standard bond, that standard running bond, right? But then the next course changes, right? And so when the next course changes, right, we have a row of headers, right, that are going the opposite direction that are tying the two wides together. Does that make sense? So we have a wide here, right? We have a wide there. Every other course has a header that ties the wall together. So now we have a wall that's 2 wides deep that's actually being tied together and working as an integral structural unit, as opposed to just a skin or a veneer on the building, right? And so the rest of these variations, right, are all variations but are doing basically the same thing, where they're trying to tie the 2 wides together and the courses together, right? So a Flemish bond looks slightly different because we don't have a standard running bond in any of the rows, right? Every other brick is turned, so it's very integral on every level, on every course, right? They're tied together. A common bond, right? This is where we have several rows of standard running bond, right? And then we have a row where every other brick switches, right? So there's our row of switching. Now we have standard, 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 till we get to this one, right, where we have a row of switching. So it's much fewer pieces that tie the overall wall together. So if we were building a purely structural brick building, which, again, I've told you a little bit in the beginning, is very unlikely here, right? Partly because if an earthquake force is acting on a building that's made up of a bunch of little tiny pieces, right, no matter how strong your mortar is, there's an awful lot of joints. So if you have just a few of those joints that aren't perfect, guess what? The whole building will start to crumble, right? Where if we had, say, a concrete wall, it's more of a monolithic building, and it can handle the stresses of an earthquake much better, right? So around here, we would typically build the building that has the structural integrity to withstand an earthquake, be that in steel, in concrete, or in wood, right? And we'd stick brick on the outside for the look, right? If we were, say, back east, where our risk is not high for earthquakes, but is very high for, say, hurricanes, right? A brick building's actually a pretty good solution, right? We have a lot of really heavy things, even in the Midwest where we're subject to tornadoes, right? We have a lot of heavy pieces that are making up our building, right? And when winds and stuff act on the buildings, we have all that weight that's going to keep it in its place, right? So it ends up being a good solution for there. So depending on where you are in the country, right, this is more or less valuable, right? So if we were actually going to build a brick building, right, what we would do is we'd first start out by laying what are called leads, right? And these are basically the corners of a brick building, right? And they're the establishment that's going to take us through and actually allow us to build the building as a whole, right? So we start with that first row down here, and we'll go through this in much greater detail, right? That first course, right? Then a second course, and we work our way up, right, in kind of a triangular pyramid pattern on the corner, right? Right, and then we string a line, right, from one corner across to the other corner, which allows us to lay all of the stretchers along here, right, at all the same level, right? So as long as we make sure our leads are correctly made and are correctly level, right, filling in between them becomes really easy, right, which is the idea. We build the center of the wall up until it matches where our leads are, and then we start the process over, and we build our little triangles on the corners, and we work our way up from the middle. Right? If you've ever seen around here, it's more common that you would see concrete masonry units, like you're driving along the freeway and you'd see them building one of those concrete sound walls. Right? Same thing happens. They build these little pyramids and then they fill in. Right? Even if it's a really long continuous wall, right, they'll still build those little leads, right, to give you guides for where they're going. Okay? So in this particular example, we're laying our first course in mortar. Okay? What type of bricks are these? Cord, right? Hollow, 60% void. Cord are just the little circles. Okay? So we build up our lead, right? After each lead, right, layer that we build up, each course, we put our level on top, make sure it's level, right? We put our level on the face and make sure it's still plumb, right? And we work our way one corner, the other corner, right? Here we are checking to make sure, right? These three bricks are in line. This one's out a little bit, so he's using the back of his trowel to tap it over just a little bit. And so there's a bit of art to how this works, bit of eye and that sort of thing, right? Again, checking all those corners to make sure they're all lining up correctly. There's not one that's out of plane, right? Once you have each of those set up, we look something like this, right? That's a finished lead, right? Then we string in between one lead to the other lead. Right? That string is nice and level, assuming that our leads are done correctly, right? And we can very, very quickly fill in the wall, right? We can stack those pieces together. Okay? Sometimes we have what are called brick veneer walls, and you've already heard me kind of talk about this a little bit. This would be the standard building practice for a brick building in the state of California built today, right? And there are a variety of internal structural walls that we might be working with. It could be a solid concrete wall. In this case, it's a concrete masonry unit wall. I'll show you examples of a wood wall and a few of the other examples. There's a couple really important things to note about these. Right? The first thing is that the primary structure of the building, right, is in this wall, not in the brick veneer. The brick veneer is just for looks. Right? That being said, these could very easily be those hollow bricks, right, because they don't have much structural value to them. Okay? The other thing that's important is there's almost always some kind of a rectangular tie or triangular tie that's going to stick out of the main structural wall, right? That's going to be embedded inside one of the mortar joints every couple courses, right? And what that little tie does is it keeps that veneer, right, attached to the building so it doesn't fall over, right? We need a way of attaching it together, so we're going to use these little ties to attach the veneer to the building. The other thing that's really critical about this is that these bricks are not right up against the building. Right? There's a little tiny gap of airspace that goes in between the brick veneer and whatever the primary structural piece of the building is. Why do you think that would be there? Rain screen is dead on, but what did you say? Okay, so not quite for the rebar because we're not actually going to fill this in. We're going to leave this as a gap. And so what you said about a rain screen is entirely correct. And we'll get to this way down the road in like the second or third last lecture, right? When we talk about exterior finishes, what does a rain screen mean? But the idea here is that if water gets through a small crack in the mortar, right, or a small inconsistency in the mortar, or through the brick itself, because it's in a really wet condition, right, water isn't going to continue through into the structural cavity or into the building itself, right? There's a gap here that allows any water that comes through to actually drain out to the bottom, right? And typically on a brick veneer building, if you look really carefully outside, you'll actually see some gaps in the mortar, right, or even some little tubes in the mortar that allow this moisture to come out at the bottom, right? So once it works its way down, it can actually escape this cavity, right? Because if it didn't escape the cavity, that would be problematic. We'd get mold, no good, right? So we'll talk about that in far more depth when we get to the exterior finishes lecture, which I think is maybe chapter 7 or something like that. I don't know. It's at the end, right? So in this particular example, same kind of a brick veneer wall. This time we're against just regular standard wood frame construction, right? I recognize certainly that this wood frame part means nothing to you yet unless you've worked in the construction field a little bit and have an idea of this. We will cover this eventually, right? Same concept here. We have these little ties, right, that are attached to, in this case, the studs, which are the primary wood structural elements, right? They're attached there. These then basically get embedded in that little mortar joint and tie the brick to the wall itself, right? There is still this gap. There's still this airspace, right? So even though we switched from a concrete masonry unit structural wall to a wood frame structural wall, still doing the same thing, okay? Different example here, right? In this particular instance, we're trying to integrate the concrete masonry units more with the bricks themselves, and we're trying to work them all together. Not going to be very common in the state of California, but certainly back east it would be valid. You're eliminating that the little metal ties that are tying the bricks together, and in this case, there's a special concrete masonry unit, right, that has a notch that's left out. We're going to put in a header that runs this way that actually will tie in, and the next concrete masonry unit goes on top of that. So we're using the bricks themselves to tie into the wall, right? That being said, there still is a gap, right? Obviously, there isn't a gap here, which is a little problematic in theory, but there is still a gap between the wall to prohibit moisture from coming in and actually working its way into the building. So I couldn't not show you at least one example of a brick veneer building, right? And of course, when I pick an example of a brick veneer building, I don't want to pick like this building because you can obviously walk around and see this building. But we'll pick one that's a little bit different, where the architects have played around a little bit with what you can do with a brick veneer building, right? And so this is in Texas. It's the University Residence Hall. This is a brick veneer building, right? It's constructed in a way that we kind of realize it's a brick veneer building because brick doesn't do the kinds of things that they're doing in this building, right? We need a way to create these kinds of cavities. I have some of the floor plans and stuff, so if you're interested, you can look at these online. Sometimes it's helpful to actually look at how they construct a building, right? And so at the end, and I recognize the projectors always never show these as clear as a laptop screen, so you can look at these afterwards on the particular slide. But by the end of this class, you could probably look at this and understand the bulk of what's happening, right? Right now, right, the only things that are really important are these little brick pieces, right? We understand that there's a structural wall behind and that there's a brick veneer attached to that, right? Likewise, if we look at a particular corner of the building, right, here's our brick veneer, right? Here's our airspace, right? Obviously a blown up detail, right? Another example here, you can see through, right, working up the side of a wall. This shows you a window opening, right? That's a window. And I'm kind of walking you through this just so you have an idea of what you're seeing, right? In this particular case, it's a window opening. This is a deliberate stepping back, right, at that window opening, which you'll see in a photograph in just a second, right? That gets you back to where the window is. That's the overhang above. There are little pieces of steel that are built into the wall that help hold these bricks in place, right? They also provide expansion and contraction joints because the building moves at different intervals in height. There's all kinds of fun stuff like there's steel truss. This is a concrete deck. You guys remember that decking, right, with the topping on it, right? Actually, we haven't covered the steel decking part of it yet, but it looks similar to the stuff we've seen a little bit, right? Right? So we can end up with something like this on the outside of the building, right? Where this would be a relatively challenging shape to try to make if it was a structural wall, right? But we have steel behind in this case that's providing the primary structure, and we can create these kinds of definitions on the surface veneer, right? Because it's only that little thin veneer, right? And so if we're looking over here, you can kind of see those little depressions that go up to the windows on the undersides of the windows. And obviously this was a lot about the exposure of that brick and that rough textured surface. Okay? So we're going to take our break now, come back at 8, and we'll continue on with the concrete masonry units and the stone part.